Good afternoon, everyone. I am Santiago Rodrigo, a PhD candidate at Technical University of Catalonia in Barcelona. I am presenting on behalf of my colleagues Sergi Abadal, Eduard Alarcón, and Carmen Almudever our work on a structured design exploration aimed at studying whether a multi-core approach to quantum computers will effectively enable their scalability. Before getting into the details, I would like to sum up the structure of our contribution. Following what Carmen has previously explained, we will firstly highlight the importance of unleashing the incredible potential of quantum computing, being the main obstacle the current limits in its scalability. We then propose a comprehensive architectural proposal, a multi-core approach including the concept of quantum network on chip, which is rooted in a communications perspective. Such an approach follows quantum computing tradition regarding its multidisciplinary research history. Our proposal then goes far beyond adding mere interconnects. We present a double full stack architecture that shows how deeply communications should be taken into account in order to really benefit from a multi core quantum computer. In order to test the validity of this approach, we use a structured design methodology to perform the first scalability analysis on multi-core quantum computers. Quantum computing has been around for quite a bit of time now. Feynman, Deutsch, and Shor laid the foundations in the 80s. However, it's been only recently that the entire world has started to hear about the revolution that quantum computing means to key research fields. As we can see in this figure, extracted from a Root 1 meter paper, the speed up of quantum computing is not a matter of orders of magnitude, but an out of this world performance. In the figure, we can see the colored lines as the performance of quantum computers when computing when factoring numbers, compared to the black line, which is the classical computer doing the same task. However, most of these theoretical results backing those amazing exponential speedups haven't been experimentally demonstrated yet. Why? Because computing with qubits is tricky. It's difficult to maintain the quantum states on them incorrupt for a reasonable amount of time. They need to be completely isolated, working at almost absolute zero temperatures. The control circuits and qubit operations are performed in a per qubit basis, and so on and so forth. In fact, integrating more than 100 qubits is right now a hard challenge, and current designs are conjectured not to scale farther than 1000 qubits. To realize how far is that from what we need to have fully fledged quantum computers, let me put a quick example. Factoring a standard 1024-bit RSA key needs around 1 billion qubits. Of course, there has been made a lot of work to break these limits for scalability, some of them presented right before me. Cryogenic control electronics, improvement on qubit gate fidelities, compiler level optimizations, etc. However, we state that the quantum leap, doubly quantum we could say, we need to overcome is calling for a multidisciplinary system-wide approach, something that may lay strong foundations for the ultimate quantum computer. Well, it may seem a very simplistic approach, but it's rooted deeply inside computer science history. If the problem is in integrating many qubits in the same chip, what if we divide and conquer? What if we interconnect many small chips into a multi-core quantum computer, as we already did with classical computers when we introduced the network and chip concept? So, we state that introducing the communications perspective in quantum computing, leading us to a multi-core architecture, will effectively enable quantum computer scalability, but only if taken as a holistic approach. Of course, putting together small quantum processors is not new. Several previous works using different qubit technologies and interconnect approaches have pioneered this concept. However, to the best of our knowledge, none of them has carried out a deep analysis on resulting performance and benefits, focusing on other aspects of the proposal, which is generally very technology specific. Our proposal goes beyond adding mere interconnects. We aim at starting from scratch a communications-driven approach for a new quantum computing architecture. With this in mind, we present a double full-stack layered architecture for quantum computing, which consolidates traditional quantum computers' layered architectures, which focus on single-core quantum computing, with a communications stack. In this figure, the computing stack is shown in blue, while the communications stack is presented in red color. The different views of the quantum computer are shown at each layer, together with the main tasks performed by each layer. This layered stack will also be the basis for the design space exploration analysis, which results we will show later on. Let us get a bit into the details of the proposed architecture, layer by layer. Starting from the top, we find the application layer. It sees the whole computer as a logic circuit with no information from the architecture. Therefore, it can stay the same for single and multi-core quantum computers. The figure at the right side will be showing for each layer the main parameters to be considered for the performance scalability analysis in a multi-core quantum computer. Both application and compiler runtime layers, being on top of the hardware, are not considered. Next comes the runtime compiler layer, responsible from adapting the code to the architecture. In a multi-core quantum computing, coarse mapping, that is, distributing logical qubits among different cores to minimize inter-core communication, is performed at this layer. However, apart from these communications-related tasks, there is no communications control yet, so no parameters for our analysis. Network layer is right below. It is key for our multi-core architecture as it is in charge of controlling the quantum network on chip and therefore the intercommunications network. The main parameters here correspond to the network configuration and performance, number of nodes, that is the number of cores, inter-core topology and interconnects technology, which will condition the communication latency and qubit rate. Communications are also very much present in the core layer. It controls qubit communication both inside the core, performed for instance through swap operations, and with other cores. Moreover, it is responsible from doing the fine-grained qubit mapping. The number of qubits per core, the intra-core topology, and the 2-qubit gate quality factor and fidelity determine the latency and qubit rate inside the core. Last but not least comes the qubit layer. Although this layer is not directly related to communication processes, its performance is key to the whole quantum computer, mainly determined by the single qubit gate quality factor and fidelity, and the qubit decoherence time. This full-stack overview of a multi-core quantum computer with built-in communication helps us to show that they play a fundamental role not only in a specific part of it, but in the computer as a whole. Without the communications block in red, the stack is unstable. But is this key block really able to unlock quantum computer scalability? This we will try to answer using design space exploration. As Medina has already explained before, design space exploration is a structured design methodology that allows to optimize a system maximizing a given cost function or figure of merit based on some parameters of interest. As it happens with any other structured design process, this optimization relies on modeling the interdependencies among the different performance metrics and the variables describing the system. This might include analytical or theoretical expressions, behavioral models, computer-based simulations, and others. It is important to note that the design space exploration is used to design, not just to optimize. The main virtue of design space exploration is to be able to consider system-wide trade-offs on different metrics that may also affect the design optimality. For example, a design space exploration analysis of a network deployment will not optimize the average throughput of the entire network, but will take into account deployment costs and qualitative characteristics such as network reliability or flexibility. Therefore, we will be able to explore the entire design space without a priorisms, not being limited to the experience of the designer, and we will be able to provide design trends and guidelines, and not only maxima or minima. In our case, we will use it to answer the questions that have brought us here. How will the quantum computer scale in number of qubits? Will multi-core approach unlock the current monolithic quantum computer scalability bottlenecks? So, to sum up, basing upon the parameter exploration we have just carried out using our double full-stack layer stack, we will abstract out the main variables impacting performance in multi-core quantum computers, apply some analytical models to it, and explore the variable space in order to extract some design guidelines and conclusions. For this first scalability analysis, we have chosen to use analytical models that would let us break the existing limits in real devices and simulators in terms of number of qubits and topology. To do so, we have developed an analytical figure of merit that models the main components of multi-core quantum performance: total number of qubits, qubit gate fidelity, qubit quality factor, communications overhead, crosstalk and other impairments among qubits in the same core. For the sake of brevity, I won't enter into details on each of these components, but if you are curious about that, we can comment on in the question time. Also, I'm available at the mail in the last slide of the presentation. Using these assumptions and models with realistic values for ion trap technology, we have performed a scalability analysis for a total number of qubits in the system varying from 10 to 10 to the 6 qubits. This analysis gives us information of how scalable the multi-core approach may be and some design guidelines on quantum computer configurations for an optimal performance. In this plot, a single core quantum computer is compared to several multi-core configurations. For each configurations, the performance, gamma, y-axis, follows a peaky bell-shaped trend, with maximum closer to the number of qubits equal to the theoretical maximum number of qubits. Trying to integrate more qubits in a single core causes a steep degradation of performance. The single core processor is clearly exceeded by multi-core approaches. In the zoom-in, the soul-like profile in the performance curve can be clearly seen. Whenever the optimal qubit distribution requires another core to be used, if available in the configuration, the extra comms overhead causes a steep fall in performance. This implies that the configuration with more cores is not always the best performing one. These two other plots contain a complete input variable sweeping, with number of qubits varying from 10 to 10 to the 6 and the number of cores varying from 1 to 256 cores. Observe that the more cores are present in the system, the narrower is the performance curve, always growing to larger number of qubits. So that's all. In a quick sum up, we have presented a double joint full stack layered architecture for quantum computers as the key factor for a comprehensive approach in the design of quantum computers by consolidating communications in the architecture to enable the full potential of quantum computing. An initial design space exploration scalability analysis has also been presented using intuitive models, from which we can draw three main conclusions. First of all, the quantum network on chip approach is actually promising as a scalability enabler. Second, for every multi-core quantum computer configuration, there exists an optimal working range. And third, the maximum number of qubits per core clearly constrains the performance of the configuration, and thus we should consider it as a fundamental design variable. With more accurate data and models coming from the multidisciplinary work of the quantum community, we postulate that this type of analysis will effectively accelerate and optimize the research on quantum computing. Well, thank you so much. Here you have my mail address. Now I will be available, but live, in real time, to answer your questions. Thanks.